Good afternoon, everybody. So let's continue with the discussion of dynamic modeling and vector control of AC drives. That is unit number 5 of the subject control of electrical drive, 6th semester electrical. So yesterday we had discussed about the vector control. So we'll quickly revise that and then we'll go to the next topic, that is direct torque control. Right. So for those who are not there in yesterday's lecture, this is the block diagram of a vector control approach. So in vector control, we assume as if it is possible to have two components of the controlling variable, D component and Q component. And we mathematically do all the necessary transformations such that D component is the component along which the flux is directed, aligned, and Q component is perpendicular to it, and it is affecting the torque, right? So here, in this way, you can have flux and torque controlling components 90-degree to each other, orthogonal to each other, and they can be changed separately without affecting the other. That is the way separately excited DC motor is controlled. And if you can control AC motor in a similar fashion, that is called the vector control. It is also known as field oriented control because we orient our field, that is flux, in the direction of D axis, right? So that way, if you do, it is called vector control. So actually what is done in vector control? In vector control, you have measurements of stator voltages and stator current. So from that, all estimations are made, all this transformation related angles, cos theta, sin theta, everything is calculated. And then you have 3-phase to 2-phase transformation, 2-phase to synchronous reference frame transformation. And then you have the actual available values of ID and IQ. So you compare with the required value of ID and IQ and go for the necessary control algorithm, and ultimately you produce the required firing pulses, PWM pulses, so that you get the required change in the torque or required change in the speed. So ultimately you are tuning the value of IDS and IQS such that you get required performance. And what is the core idea? The core idea is that you would like to keep machine flux constant and you would like to change the torque to get the required speed, right? If speed is less, you would like to accelerate. If speed is more, you would like to reduce. And if speed is required speed, then you would like to continue in a steady state with that particular speed. So that is the principle of vector control. So with this background, now this is what we have already discussed. So we are not advantages we have already seen. Decoupled control is possible, fast dynamic response, and speed sensorless control also possible if you wish to have. Disadvantages is something which we will discuss slightly later, but disadvantage is it that you require a very fast processor because all these measurements, all these estimations, transformations need to be carried out in a one sampling interval. So sampling, if you take samples very slowly, then again the performance will be sluggish. And if the sampling is fast within the duration of these two samples, you have to do the whole, complete the whole control action. So then only it will be real time. So anyway, so fast processor is required. It's a complex method, requires transformation and all. And that is the only challenge we have for the vector control. There was one more method developed known as direct torque control method. And today we would like to go for this method, right? So before we go into the details of how direct torque control method works, you need to understand the concept of the space vector or switching vector. This method is applicable only to the induction motor drive which is operated by voltage source inverter, right? So when you have an inverter operating the motor, by controlling these switches, suppose I have a 3-phase inverter and it is a 2-level inverter, so I have a 6 switches, 3 in upper leg and 3 in a lower leg. 1, 2, 3, 4, 5, 6 is what we name them. So just by controlling those switches, we can generate a particular voltage space vector, And by selecting or by generating that particular voltage vector, we can control a particular value of torque or flux. And that is the objective of direct torque control method. How we can do it? That is what we are going to discuss today. So this is the concept of space vector. So if I have three vectors, ISA, ISB, and ISC, that is ABC three vectors, then I can mathematically combine them and represent it as a common vector, say IS, which is nothing but as it is shown 2 by 3 times ISA plus A times ISB plus A square times ISC, where A is a operator which is multiplied by this vector. It is e raised to j 2 pi by 3, right? That is nothing but the phase difference. So in short, instead of having three different equations, IA, IB, IC, I can represent by a combined vector at any instant, which is given by this expression IS into e raised to j omega t, right? So this is basically representing at any instant the resultant of these three, right? So this is how reverse way, if you have IS value, you can find out ABC values from this. Real part of IS is ISA, real A square times IS is B, and real of A times IS is the C phase current. Right? So this is called a space vector. Now, how basically these things operate? So this is our three-phase inverter, which is nothing but two level. So you have you have six switches, three in upper part of a leg, and three in a lower part of a leg. At any instant, you know that any of the one switch is on in a leg. Say this is first leg, so either first or fourth is on. Is same with the second leg, either 3 or 6 or 5 or 2 is on. Both the switches, if they are on, then it is going to create a short circuit. Both the switch, if they are off, then it is going to create a zero vector, right? So when a switch is on, ultimately how much voltage you get across a phase, say A phase, B phase, or C phase, that will have certain amount of DC value, right? So let us assume you have a situation known as 100. 100 means in first leg, top switch is on, that is 1 is on, Q1. In second leg, 0, that means bottom switch is on. And in third leg also 0, that means bottom switch is on. That means Q1, Q6, and Q2, these three switches are on. So when this is on, ultimately the resultant diagram is in this fashion. You can see positive over here, A, then B, and then C over here, similarly over here. So these two will, suppose Z is the impedance of this that is motor per phase. Each phase is having impedance Z. That means these two will come in parallel and positive is applied over here. That means the voltage VD, which is appearing across A phase, you can very well find out using potential divider rule, that it will be 2 VD by 3. And over here, the voltage will be minus VD by 3, minus VD by 3. That means 2 VD by 3 over here along the direction of A axis, minus VD by 3, that means opposite to VB, and minus VC, that means opposite to VC. So if I find resultant of these three, this is 2 VD by 3, there is A phase, this is B phase, and this is C phase. So I get a resultant vector known as V1, which is known as a switching state vector with the switch position 1, 0, 0, right? 1 means when top leg is on, and 0 means bottom leg is on, right? So first switch, first leg, second leg, third leg. So this is the switching voltage vector, resultant voltage vector generated because of the switching of 1, 0, 0. Likewise, all possible switching voltage vectors are shown over here. We can very easily show. I am not going to waste my time in explaining each switching vector. This is a very little exercise. You can do it yourselves. So when you have different combinations, which switches are on is shown in the table over here, right? So likewise, I have a 6 active switches where you have a non-zero voltage vectors, N2 0. That means when all 3 are on or all 3 are off. So these are the vectors where you have zero voltage. So V7 or V0 is called null vector or zero vector, where the resultant voltage is zero. Otherwise, you have V1, V2, V3, V4, V5, V6 in the direction is shown, right? V1, V2, V3, V4, V5, V6. That means by switching a particular switch combination, I can generate a particular switching voltage vector. That is the fundamental which you are supposed to understand. Now we are going to make use of this knowledge, right? So now direct torque principle tells me that torque is nothing but interaction of two fluxes, stator flux and rotor flux. The fact is that stator, whatever voltage you apply on the stator produces stator flux, and rotor always follows it. So stator flux is always slightly ahead of the rotor flux, right? And there is a gamma angle between them. That is called gamma SR, right? Stator rotor angle between stator flux and rotor angle, gamma angle. If I can increase this angle gamma, see if this everything else is constant, if this angle increases, torque increases. Torque is proportional to sine gamma, I can say. And sine, as you know, sine 90 degrees maximum, sine 0 is 0. That means by increasing this angle, I can increase torque. By decreasing this angle, I can decrease torque. So this angle is nothing but angle between two fluxes. So, if I can change the angle between stator flux and rotor flux, I can increase or decrease torque. And I can always change the value of fluxes as per my requirement. But generally, motor control is done with maintaining constant flux and changing torque as per the requirement, right? So how is it done? So this is the KVL equation of any phase, right? Vs is equal to ISRS plus d by dt of the psi s. Psi s is nothing but the flux linkages, n phi, which is equal to Li. So if I neglect the resistance drop, what do I get? V is equal to d psi by dt, right? So that means if I take a small, for small interval, the delta psi s is nothing but Vs into delta t. That means the change in flux vector will be whatever is voltage vector, which is operated, which is there in force, which is active for small delta time t. So by selecting a proper value of Vs for a small interval delta t, I can change the value of delta s. That is, I can increment, decrement, I can change magnitude, or I can change angle. Now, how can I do it? That is what we are going to change. So this is the formula which is there in the red. We are supposed to understand. You can change stator flux by selecting a proper voltage vector for a fixed interval of time delta t. Look at, now let's assume the situation that my stator flux is over here and rotor flux is obviously slightly behind it. Right? So I have not shown over here, but it is always behind it. Now, if I want to increase the torque, these are the voltage vectors. This is 3, this is 2, and this is 1. If I select any of these 3, ultimately this is going to advance. That means the stator flux is going to have move in this direction. So rotor flux and stator flux will have a more angle, so torque will increase. If I select the value like this 2, 1, or 6, then the resultant stator flux is going to increase. See, this plus this, that means the resultant is going to be increase. So flux will increase. That means, do I want to increase the flux or do I want to increase the torque? Do I want to decrease the flux? Do I want to decrease the torque? Based on my requirement, I can select any of this switching vector for a small interval delta t. You can see I have given a table over here that in this particular situation, जब stator flux यहाँ पे है, उस वक्त what switching voltage will happen, will result into what? See, V1 will increase the value of flux but decrease torque. V2 will increase the value of flux but and increase the value of torque likewise. So likewise, I have a table that based on the location of stator flux, which switching voltage I should select if I want to increase the flux or if I want to decrease the flux or if I want to do the other way around, right? So that is the fundamental of a direct torque control. Now look at the operation of direct torque control. So what do you do over here? That I have a speed reference. I measure the actual speed and give it over here. Depending on the speed controller, I have a control signal, and that is processed by a limiter block. So over here, I produce the required torque. Yeah, my speed is suppose less, and I need to increase. So this is the torque at which I should accelerate. So this is my required torque. This is actual torque. Actual torque I can calculate if I have value of stator currents and stator voltages that we have already discussed in our yesterday's class. So this is torque error. Torque error is processed by a hysteresis band torque controller. Hysteresis band torque controller means whether torque error is within the limit, less than value, or greater than value. If it is greater, it will produce error +1. If it is within the band, then it will produce the signal 0. If it is less than the band value, then it will produce -1. Similarly, I have a reference flux, which is the value of flux which I should maintain constant. This is the estimated or calculated value of flux. If flux is within the limits, it is all right. If it is the error is more, that means +1 is there. If error is less, it is -1, right? And this is the angle of state psi s. As you had seen in the previous slide, I need to find out where exactly is my stator flux vector. Then only I can select a particular voltage vector. So these three information if I have, then based on my switching lookup table, I can select that what voltage vector is to be selected. Suppose I select voltage vector V1, that means which switches are to be turned on is directly indicated. So just firing is to be given to those switches. So the control becomes very, very easy. So based on this three, a lookup table directly selects which switches of inverter has to be turned on. So this is repeated in a particular manner so that you get a required torque, you get a required flux, and you get a required speed. So directly you are controlling torque without any complicated transformations or some complicated calculations. These are the estimations. If you have the value of ABCs, this is a switch position. If you know the value of VDC and which switches are on, from that you can calculate ABC. Then you can calculate DS, QS from the transformations, and then this remaining calculations very easily you can estimate. You can see only stator resistance is required in all this calculation. All other values are nothing but the measurements carried out, right? So this is the control strategy which we were talking about. If Xi is equal to 1, that means required torque is less. I need to produce more torque. So I need to increase torque. Similarly, Xi is equal to -1, that means required torque is to be reduced. Likewise, I have a torque, sorry, this is for flux and this is for torque, which we already talked about. Whether you want to increase the flux or decrease the flux, based on that plus or -1 is generated. If you want to increase torque, +1, decrease torque, -1, or if you want to maintain the torque, then 0 is to be generated. The value of torque is 1, 0, -1, value of flux error is 1, -1, and the position of the stator vector can be in any of these sectors. What are these sectors? The 360-degree plane is divided into 60-degree segments, right? Segments are over here. This is -30 to 30 is the sector 1. Then this is sector 2 and this is sector 3. Likewise, the whole plane, two-dimensional plane, DSQS plane, is divided into 6 sectors. So if I know that my stator flux vector is in sector 1, and I need to select a switching voltage vector such that torque also increases, that is this one, and flux also increases, then this table recommends that select voltage vector V2. What is V2? V2 is this. That is, turn on the top switches of leg 1 and leg 2 and turn on the bottom switch of leg 3. So directly you can give this switching signal to inverter, which switch is to be turned on. No PWM signals are required. Directly you give the switching commands to switches. Okay. So then necessary change will take place. Again, you read all the values, read the generate these errors, and accordingly the lookup table will select any of these switching vectors. And these switching vectors are directly switching commands. Based on this, very easily you can switch on or switch off the legs of an inverter. So this is how a direct torque control takes place. So actually what happens, so this is the band, hysteresis band, in which by selecting appropriate values of vectors, it will remain in this band, the stator flux, right? And by tracking this, you will get required flux, you will get required torque, and you will get required speed. So this is known as a hysteresis band. So you can have a very decoupled way. Decoupled means you can select, you can see, depending on your requirement, you can change the value of flux, whether what to do to increase flux, increase torque. Independently, you can select. So decoupled control is possible without complicated transformation. So this is called the direct torque control approach. Once again, this is the table which is showing you for a particular position. अगर sector 1 में हमारा stator flux है, so which voltage vector should I select to increase the value of flux or decrease the value of torque and something like that. So all different combinations are shown over here. Mind well, vector control and direct torque control are advanced modern methods generally applicable to PG students, master students. You are, as an undergraduate student of control of electrical drive, should know the basics of it. So it may happen that all the details or intricacies of it you may not be able to understand, but the overall idea you should have about how the vector control or direct torque control method is working. You are going to learn it in detail in your PG courses if you select this subject as your major course. Right? Now, striking features of DTC. It is very simple to implement. You can see you only require 3 voltage, 3 current measurements, simple calculations, and then you can directly decide which switches are to be turned on. It gives high dynamic performance because again you can have a decoupled control over here, but without any complicated transformations. No current regulators, no speed sensors, not depending on motor parameters. Speed sensors are there also, that is all right. If it is not there, you can calculate speed. No depending on motor parameters. If you had concentrated on the equations, you only had stator resistance in this particular calculation. So no other calculations were there, no other parameters were there. The problem is that you have a hysteresis band, so on-off type of control will be there. So there is going to be some ripples in the torque. If you want to take this hysteresis band narrow, you require fast switching. You require a switch which are able to operate quickly, and you require controller who can compute quickly, right? Switching frequency is going to be variable. That is a problem, and poor performance at low speeds. These are some of the challenges on which research is going on. Now, if you want to compare the two approaches, vector control is vector control, of course, while this is a scalar control. Here you are not basically controlling any angle as such. Indirectly, it is controlled. This one is a complex method, requires all motor parameters. This is a simple method, does not require, it requires only resistance of the stator winding. This is a complex transformations required over here. Here, simple calculations are there. PWM generators are required. Here, PWM generators are not required. Directly switching is done. This gives high dynamic performance, while this is giving you comparable performance, but there are torque ripples. So it's almost vector control like performance, far better than the normal V/F control method, DTCs. This one is a costly and a fast controllers are required. This can work with little less costly and little slower controllers, right? So this is all about the chapter dynamic modeling and vector control of vector control of AC motor drive. So here I stop for this, conclude this chapter over here. From next week onwards, we are going to start with the last unit, that is solar control drives and battery operated drives, right? So thank you all. If you have any questions, you are most welcome to spell it out